Good day to all of you. I, Wicent C, on behalf of my co-authors Nigel, Lovell, and Redmond, will be presenting about our paper entitled Tracking Lower Body 3D Kinematics Using 3 IMUs. Motion capture is the tracking of the human body, where the system estimates the joint positions and orientations of body segments. It has a wide range of application, not limited to animation, robotic teleoperation, and virtual reality. Our paper focuses a bit more on clinical application, specifically on gait analysis, which is the study of human movement. Some example of its application is in geriatrics, where research studies have shown gait parameters are good indicators of fall risk. It can also work in conjunction with gait-assisted devices, where these devices can provide real-time feedback, such as haptics, which can help correct movements for better stability. Can also be used in sports for performance improvement and injury recovery. Motion capture can be done using camera-based systems, which is also the current gold standard in the industry for motion capture and can reach millimeter accuracy, albeit limited within a limited capture volume or in a small space. There are a lot of potential for capturing motion in the subject's natural environment, including 1, better understanding of the disorder evolution, 2, the potential to allow early intervention to prevent the disorder or that movement disorder from becoming worse to begin with. Hence, it is our goal to develop the technology to enable remote gait analysis. Now, recent trend of technology is the miniaturization of IMUs or inertial measurement units. These IMUs are capable of measuring acceleration and angular velocity, giving us position and orientation estimates. Albeit there is a little bit of some noise in there and causes a bit of drift in the estimate. Now, IMU-based motion capture systems, specifically those that puts one sensor per body segment, can have demonstrated that they can capture motion almost everywhere, albeit still a bit too conspicuous for everyday use. Researchers have taken many approaches in solving this problem, some of which uses soft stretch sensors to capture movement, more and smaller IMUs spread throughout the clothes or wearable on your garment. And not the least is to use sparse configuration or the least amount of sensors possible in hopes of comfort. This paper will be focusing more on that. So again, the goal is for comfortable, fast, and accurate motion capture systems. And these are challenges associated, there are challenges associated with sparse configuration. In a one sensor per segment setup, each IMU tracks the position and orientation of each body segment. Now, if we use less sensors, we lose information on the uninstrumented body segment. To cope, there are 2 ways in general. First is to infer the state of the uninstrumented segment through biomechanical constraints from the state of instrumented segments. Second one is to infer the state of the uninstrumented body segments through additional measurements. This paper will be focusing more on the former type, where we infer the state of the uninstrumented body segment using biomechanical constraints. Now, in tracking pose and applying biomechanical constraints, the representation of the pose plays a crucial part. There are many ways to represent pose. Tracking position is typically straightforward, but tracking the orientation or rotation is not quite. Tracking orientation using Euler angles have singularity issues, which means there are certain configurations where it will fail to track, while tracking using rotation matrices and quaternions is a better solution, as it doesn't have singularities issues, but it has a limitation where you cannot treat it like a vector. Indeed, you cannot add 2 rotation matrices together and still have a valid rotation matrix. You will need to use additional constraints. But when you apply this constraint, it may not necessarily, depending on the formulation, it may not necessarily make geometric sense. The focus of this paper is to use Lie group with rotation matrices, which allows for a more elegant way of representing rotation in the vector space. This paper builds on prior work where we track lower body segments, specifically the pelvis, thigh, and shanks, using 3 IMUs placed on the pelvis and ankles, and using a Lie group constraint Kalman filter. The Lie group Kalman filter, as formulated by Barmode et al., tracks the position of the pelvis and the shanks. In this version of the algorithm, or in this paper, we use the same framework as the 5-segment counterpart, but instead, now we track 7 segments, and we have the IMUs on the pelvis and on the foot. So foot instead of the ankles. Similar to before, the algorithm has 3 main parts: prediction, measurement, and constraint update, with most of the changes in the measurement and constraint update. The post-processing also had a lot of changes, where instead of 2 segments before, we now infer 4 body segments, specifically the thigh and the shanks, from the pelvis and the foot pose. The animation shows what each part of the algorithm does. The prediction step takes an IMU input and propagates the state through kinematic equation. As you can see, it is able to track the body segment about drifting from each other. The measurement update uses the orientation estimate from the IMU, a couple of pelvis pseudo-measurements, the flat floor assumption, and zero velocity update to estimate body pose, and you'd see it looks a bit more human, but with that weird leg lengthening. I would like to note that the measurement update for this 7-segment algorithm is a little bit more stricter compared to the 5-7-segment algorithm before. Lastly, the constraints update, where we had leg length and the hinged knee and ankle joints, makes the walking animation a bit more human-like. Again, I'd like to point out that there's a significant change in the constraint update, where we have less constraints now from 3 to 2. And that has something to do with because we have more uninstrumented body segments, more unknowns, and hence we can only enforce weaker constraints. Because if we enforce the same amount of constraints as before, we might end up doing the wrong assumptions. More animations comparing the 5-segment algorithm to the 7-segment. The prediction step has the same issues where all body segments are drifting away from each other. You can see that in the measurement update of the 7-segment, it looks a lot better than the ones in the 5-segment. And that is because, as I mentioned before, the measurement assumptions are more stricter than before. And in the constraint update of the 5-segment actually plays a bigger role back then than in the 7-segment. So we tested this on actual IMD data from the sparse CKF dataset obtained before for the walking movement. Again, similar to before, most of the deviation is in that turning motion. You also have this smaller bumps being lost in the knee joint angles. Below shows the joint angle RMSE and correlation coefficients with the knee, hip, and ankle joint angles. The L7S3 IMU signifies actual IMU data, while the L7S3 SIM signifies simulated IMU data from the Vicon dataset. The NRPIG, or plug-in gait, is the benchmark obtained from the plug-in gait module of Vicon, which is typically used in gait analysis, while the NRK fit, or kinematic fit, also obtained from the Vicon dataset, but using a benchmark model that's typically used in robotics and animation. You can see from these 2 benchmark results that they are pretty much the same, with the primary difference in the hip, or in the z-axis, where there's more error in the PIG than the K-fit. And this does make sense because the kinematic fit uses the same underlying model as our Kalman filter, specifically the hinged knee joint. Comparing the tree IMU and the tree sim, we can also see that they are quite comparable, which tells us that this approach is indeed promising. The sagittal joint angles were also good, although the ankle sagittal joint angles could use a bit more improvement, but we do expect this degradation in performance because in the usual model, ankles have 2 degrees of freedom, and in our Kalman filter model, we assume that there's only 1 degree of freedom. Some bonus preliminary work or animation for the dynamic movement. So you have high knee jog and jogging on the right. And now you also have jumping jacks and speed skater. It's good to note that once we do run the dataset, because we have a more stricter assumptions in the 7-segment version of the algorithm, although the animation looks perfect, we do expect that there's an overall performance degradation when we run it for the full dataset. In conclusion, this work does shows that there's that 7-segment tracking using tree IMUs is indeed possible, and that Lie group representation is a promising approach. Please check out the link for the source code and data of this work. And as part of future work, we would be interested to try using even less sensors or additional measurements or sensor types. Please do check out that paper, that journal paper, which provides more information about our work here. Thank you for listening.